This conference will now be recorded.
Okay, good morning, everybody. Somebody just joined. No. Callum Devlin. Hi, Callum. Let me just pop you in.
Morning.
Okay, hi, everybody. Right, so today, in terms of first order of the day is new attendees. I don't believe anybody's new. It's on? No. So we'll just move straight to item number 2. So as I sent out an email, we are making some sort of steady progress now on these two of the 3 modules at least. The IBM Power 10 one, I've got further discussions going on there. There does seem to be a lot of work to do there, but I think we're making progress to be able to get started on that one. And the Xilinx Versal FPGA, the VP1802 module. So that one's beginning to take shape as well, and I'm making some progress on that one as well. But as we get into the more of the details of this, we're going to want to start to pull in additional volunteers and expertise to actually help us move the ball forward and actually turn these things into reality. And so what I've tried to do here is list the immediate things that have come to mind for me, maybe either from who we have here or contacts we have, we can encourage others to come and join us and actually help us to move this ball forward. So and as well as that, on the third agenda item here is really, I want to take a leaf out of the OCP ODSA's workbook. BAPI's done a pretty good job of trying to get a forward-rolling agenda of saying, well, what topics do we want to be covering in future meetings, and hopefully, as maybe we do get some more contribution, we can get maybe, like, for instance, on power, we could get some power supply companies to come along and say why they think their power solution may be good, and if we can get some silicon companies to actually provide, power silicon companies to actually provide maybe a power tree recommendation for these 2 modules, then that would be great. And again, with interested parties that start to believe that we're getting this momentum behind this, if they can get their components designed into the early reference designs, then that gives them maybe a good opportunity, a good commercial opportunity to be motivated to help us out. So good old open community trying to pull everything together. It's going to be, I'm sure it's going to be a bit all over the place, and we're going to be short of some resources, but I've been fairly successful. I can in sort of at least talking to some initial companies and getting some basic interest. But I'd like to all of you with your various connections, or if you can maybe provide some ideas, that would be good. So maybe I've got some very minor updates on some of the progress. Let me maybe just jump to that right now. So on the actual modules, the Power 10 one is the basic layout, the assigned interconnects that I've actually got for the Power 10 single chiplet package. So the key attributes of all of these are, we need to basically, the module, every IO of this Power 10 device is effectively connected to one of these connectors. But we've got the boot. We've got to be able to boot the processor. So there's a whole bunch of sideband management and booting. I think it's called LPC. Is that right? Top low pin.
Yeah, I mean, there's a low pin count interface. Certainly, it's involved in getting everything up and running. And, certainly other things. Well, there's a self boot engine on there that that does part of the boot, loads the host. But yeah, you need the low pin count interface. You need the connections from the BMC or BMC like entity into the self boot engine to kick it off, and you need the connections also from that same entity into a power sequencer, something on our standard systems that would bring up all the rails in the right order. So there's a lot. Yeah, there's a lot to discuss.
Lot of sound band. Yeah, it's the same. It's the same stuff on all of these things, I guess, basically. But the processor needs to get off its knees, and so there's a lot. Obviously, there's the BMC, the board management controller, I guess, basically controls all of this. And so, and Todd, for those of you that are at the last meeting, Todd went through the Open BMC, the Libra BMC, which is the hardware implementation, and the what they call DCSCM, the security module, which is the actual physical format of what carries the Libra BMC circuitry and what runs the Open BMC software. So we need to. I think we've moved the ball forward. We want to implement Libra BMC actually on this module. Todd and I had a chat about this, and we want to bring this up as a standalone processor. So let's not worry about we want dual socket or quad socket or whatever. We want to just bring this up as a single socket. So we've got the power supply bring up with power supply management. We've got the boot management using Open BMC. And so that's the basics there. So I mean, we're beginning to get a block diagram, or I am certainly from talking to Todd and others, of what we need to do here. And then there's a software level of getting that boot up and running. And that's hopefully where maybe this is where we can recruit open source resources. And I guess the wish I've got here is a bit like the Linux Foundation started. We're a hardware equivalent to the open source foundation. The challenge we have is that the software world, there is no cost. It's just people's desire and effort to bring some of these things to the open world. We unfortunately do incur costs, and to get these things to physical reality. But on the basis we have motivated parties that see this as a good thing, certainly on the silicon front, and can actually maybe financially benefit out of supporting this open standard, then I'm hoping that we can get some support out of the woodwork. As well as that, we obviously we will need some funding, I believe, to really get some of these things, give them a bit of a boost at the beginning. So this is a Power 10 one. So that one's progressing steadily, and we are getting support from Open Power, etc., to actually start to bring the information we need to start this, to get this hardware ball rolling at least. On the FPGA side, I've been doing a little bit more. So in the block diagram we showed on the FPGA side of things, we were talking about maximizing the memory footprint here, and so this one had 32 channels of OMI memory on it, but it had reduced topology interconnect. And so I've been looking at a couple of other use cases, and I thought that it might be better to balance things out. I mean, this doesn't need to be nailed right now, but I'm trying to get down to an interconnect architecture here that gives us the best flexibility. And so I've made a few choices in terms of these potential to support OMI memory channels, 2 per socket. I've reduced this down to 20 OMI channels from the 32 of the big system block diagram, and I've given ourselves the ability to have all of the 8 lanes on the topology interconnect being capable of running at 112 gig. So they would go down to 4 lanes at 112 gig because you get every transceiver, or it'll be 8 lanes at 56 gig on these. So So this would give us the ability to maybe connect to 800 gigabit Ethernet to QDDs or OSFPs, or 400 gigs in QSFP type cages. And you will see the way I've configured the PCI. I've made a few changes there. I've got the 8+8 put into the BICE16 connector, and it's also NIC 3.0 capable, so you could do a NIC 3.0 card straight in there and to network cages. So that was one reason. You could plug a cable in here, so you could connect to the OAI chassis host interface board with just one cable connector. So that was a reason for putting those two together. We've got 2x4s, meaning we could pop a couple of NVMe drives in on the other ports, or communicate to something else over PCIe. And then these other ones, these are absolutely obviously fully programmable. These ones based on IP. So basically any E3 module, a CXL, .mem, an OMI, an NVMe SSD, we should be able to put anything down in those with the appropriate for IP in the FPGA fabric. And obviously these 112 gig links could talk Ethernet or a whole host of other interfaces, depending on, again, the IP. There is one other thing that when I was going through, just while I was going in a bit more detail on the FPGA, I've been doing some power analysis, which is, and this is available. So one thing to bear in mind actually on this particular FPGA is this is in engineering silicon realm right now, and it's part of what they call the early access program. So you've got to have signed an NDA to get all of the early access details. So obviously on this forum we can only share what is public, but the power estimation tool is actually public. So I can share with you what we've done on the power side. These FPGAs do have quad-core ARM SoCs on board, and so there will be a little of probably an LPDDR4 chip or two on board on the module itself to actually give the memory, give the processor some local memory to boot up. So that'll be one adder to this block diagram. But essentially, again, it would be good to have Libre BMC on here, you know, and have OpenBMC running in the processor. So that would be something we'd need to do to bring this processor up. It's inside this to make it a standalone unit as well as a pure accelerator. And obviously we need the power supplies, so I think that covers, and obviously the clocking structures, and we need the clocking structures as well on the Power 10, obviously. Just on the power supplies, this is the Versal full-blown power block diagram. You can see there's a lot of power supplies. It does boil down to a handful of voltages, but there, you know, it still is quite a bit on the power front that we need to do. I did actually, let me just, this is the power estimator tool from Xilinx. And so in the summary sheet, you can see I've done some power estimations. I've done this for a living, so I always go very aggressive whenever we've designed a card in the past. When I was, you know, with Nalitech, my company way back when, we would always, our customers could program any bit stream in there, so we design the power supplies to take in the real worst case scenario, and we were usually you know, pretty conservative in terms of what we did. So just a couple of things here and this. We've gone for the highest speed grade, the highest core voltage. We've assumed we've got a junction temperature on the FPGA of its maximum 100 C, so therefore we've got the worst case leakage. We've got the worst case process. We can see that we're at 400 watts on this implementation. There's a bunch of other stuff that you go in. Basically, I use 80%. I assume you can use 80% of the resources of everything, which is again highly unlikely. Only the mad guys they can really push the FPGAs take anywhere near this level. My experience is probably 50% loading of this is more typical. But people can get up here with a lot of design effort. So you're using 80% of the DSP resources, etc. The I/O, I've specifically configured the I/O channels to be what we've got in that block diagram. And that's where the power. So then you get a power tree. So we can give this to the power supply companies and try and get a power supply tree if we can convince a power supply company to help us out on the power design. You've got all of the tolerances. You've got the AC ripples. There's some really tight ones on the analog supplies to the transceivers. So a nice challenging power tree. But we have this. So this is now this is my baseline. For the power supply design, and if anybody has got more experience on this or has a different view, then but I think a power supply that can deliver as 400 watts should cover just about every use case of this FPGA. So that's where we're moving the ball forward and starting to get into the real design. So that's why I'm moving on to where can we get additional support. Any questions?
Hey, Alan?
Yeah.
Alan, can you hear me?
Yes.
Oh, cool. Okay. I was just I dialed in through the phone and the computer, so I didn't quite understand the mechanism of the talking. Okay, cool. Yeah, so we are developing at least one of these modules for at least one ASIC right now, with a power supply, et cetera, et cetera. So we are looking for additional support with especially the sideband controller element to it, portions that we're not that experienced with. Obviously the power management we're happy with, the thermals we're okay with, and we have the pinout of the ASIC, device target SoC that we're going to use. But we're kind of like, well, we might as well just build the whole thing instead of, we were just going to make it for a load test tool. Then we thought, well, we're going to have, we're going to be halfway there. We might as well do the whole thing, right? So
okay.
We're talking about putting in a mechanical back plane with the cooling plates, et cetera, just by busting the 48 volt, just going for the whole deal. But we are looking for additional support from the community in terms of design support. I mean, we've got, our CAD is fired up and we're moving forward, but we would like, if we're to make it the complete working solution that's demonstrable, we need help from the other vested parties.
Right. And so your for these current silicon power supply projects you've got going on, you're choosing the format, the HPCM format for these testing vehicles you're building. Is that what it is?
Yeah.
Okay, great. All right. This silicon you're talking about, can you give any more details? It's not the ones we're building right now here, is it?
It's I'm not sure if I'm allowed to say. It's a programmable device. I don't know if I'm allowed to say. That doesn't really tell you much, does it? I think most devices are programmable. It's a big. I need to just check before we can disclose it. Or yeah, I think it's in the public domain, but I need to check that. Forgot about the size of the audience, so let me just check that.
And you guys, you do the load slamming side for those that don't know, right? So you do the testing side of power integrity, right?
Right.
So you make the adapters. Load Slammer, Roger's company makes adapters. So they'll make a chip that's got the same footprint as your processor. For processor companies, they will make a chip that will solder down on exactly the same site as your processor solders down, and then be able to give load slamming effectively on that device, and so you can actually mimic what the processor spec is, and actually see that the power supply that's been designed works to the requirement of the silicon.
Right.
And the beauty there, yeah, I was just going to say the beauty that me from a customer perspective is when you get a problem, you know, the silicon vendors, as a systems guy, the silicon vendors say, well, your power supplies are rubbish, and then, or your signal integrity is rubbish, or your clocking is rubbish, and it's a nightmare to solve the problem. And sometimes you say, is it your engineering silicon that's rubbish? And it takes you 6 months to prove that your board is great before they'll even look at their silicon. And so testing tools like this are really good. This is why these adapters are good. So Roger, so you're using the HPCM format for showcasing some, and I guess you partner with power supply companies as well, right? That want to feed these silicon devices.
Yeah, so we've worked with several module companies and the usual multi-phase vendors out there: TI, Infineon, Renesas, MPS, and then we also use a bunch of different modules based on what's the most appropriate. And the whole concept is that we're going to validate, you know, a power supply in this form factor with one of the big three SoC players. Yeah.
Okay.
Yeah.
So
maybe two of them. I don't know. But we need to, we can get it, you know, from a power and signal integrity perspective. We want to do the testing, but if you get that far, you might as well just slap a chip down and call it done, right?
Right. So okay. So in terms of the power supply side, do you think you could attract any of the power vendors to? So we have. Talking to Vicor. I think I mentioned this a few weeks ago. We're talking to Vicor. At the moment, so they were interested, but at the moment I've not got any more traction. I've lost my contact in there basically. So I'm not too sure if we can convince Vicor, unless somebody else knows people in Vicor that could help out. But there are other power solutions, right? So I used to know the people at MPS. I'm going to try and dig up my contacts there and get to them. But you work with some as well, right, Roger?
We have a known good solution right now from the Power Stamp Alliance.
So who's that? The Power Stamp from?
Yeah, so that's like ST Micro with Artisan, Bell, and Flex, I think.
Artisan, Dell, did you say? And Flex?
Bell for Bravo.
Oh, Bell. And Flex. Okay. Okay, great. All right. So that could be they could be one of the people that can bring a power solution to this.
Yeah, I mean, we've got it in the CAD right now. It looks like it'll work. We've used them before. So
we would need to align their power to let's say like this FPGA power footprint that I've just created. If we could.
Yeah. And that's the Versal, right? We could do it for the Versal. That's not a big deal because we're part of the Alliance program. We're an early partner there, so we could cut that in, no problems.
Okay. Well, this actual power tree is open. The power tree I just showed is just downloadable on the website. You don't need to be.
I'm talking about more like the ball out specific. But yeah, of course we can. You know.
Oh right, yes, yeah. To build an adapter, right? Okay.
Yeah.
Okay. Right.
I mean, Virtual's definitely on our target list.
Right. Okay. So I guess it's, can we get a an adapter designed for that?
Yeah.
Okay.
I mean, I don't see why not. We just need to make sure that there's the, if we're going to do it, we really want like that, all the support from, you know, the community to do that.
Right. Right. Okay. All right. Well, that covers the power supply. Is anyone else know any good power contacts? Anyone well connected where maybe a power solution provider would be interested in helping us out?
Can you send out an email or something I could forward?
An email for what? Sorry, you talking to Roger or?
Just generally, if Alan yourself, if you could send an email, I could forward to people I know at the IEEE Pels group.
An email requesting.
If you just general request for help or participation, and I'll just forward it to people I know in the IEEE Pels.
So okay, all right, okay, excellent. All right, thanks, Kevin. That's great. Okay, all right. Jumping back to so thanks for that, Roger, much appreciated. Jumping back to obtaining funding. So I've slipped this one in here. Clearly, if we can get the funding ball rolling, that would be good. I'm hopeful we can get government support somehow, but I'm still exploring that. Oh, by the way, I see that Zed has just joined us, so say nice to see you, Zed. So I guess on the funding side, we do have, so we've got interest from some of the labs. I've had interest from the DOE. Somebody actually approached me from the power efficiency side, and I think somebody here on the call mentioned touching base with, there's a lady that presented to us almost a year ago, probably now.
Natalie Bates.
Natalie Bates, thank you very much. Yeah, Natalie Bates did, and they are specifying efficiency requirements of HPC machines. In fact, I had a very interesting conversation just last week with one of the members there that's taken an interest in HPCM, and he said they're trying, the power supply of the grid can be played havoc with the power supply of the grid an HPC data center does. So those of you, if you know much about the electric grid, there's something called power factor correction. So when you get big inductive loads like motors, etc., you know, this is a historical thing. You actually screw up the efficiency of the grid supply. So you have special circuits that compensate for this to make sure, called power factor correction circuits, that actually balance the load. Well, part of the problem is this massive on-off demand of processor chips, you know, unpredictable ones for certain applications, can play the same havoc with the grid is these inductive loads. So this chap I was talking to does the analysis from the grid all the way down to the 0.8 volt supply, providing 500 amps to the processor and being turned on and off at the nanosecond level. Part of Natalie Bates's group is an actual desire to measure the efficiency down at the lowest of levels, you know, so that you can actually build a full model or a full picture of the load characteristics of a particular application and a particular type of silicon. And that's because it's a big efficiency drive. That is a heavily funded area in the HPC space. And what we can potentially do is this open BMC. Well, another thing is IBM have done an awful lot on this, and IBM have, in fact, Stephen Roberts, when he was with IBM, presented at the OCP Global Summit, not last one, but the one before for me, and he was talking about some open standards that they were trying to push, because the HPC community every year, every installation almost start from scratch with the system management of their HPC machine with each different vendor. And so trying to standardize around the power measurement and this sideband management could be a nice funding avenue to help us get these projects off the ground. And so that's one particular one. And Todd's helping me inside IBM in terms of potentially the research groups there. Could we get funding vehicles via the bigger companies coming into OCP, or can we get sort of more sprinkled funding and do it with OCP? So that's the other side of things I'm trying to push through. But anybody, I see that we don't have our friends Bob COT or Trent John.
There's an IEEE effort or two in that space. So there's a whole thing in blockchain energy transaction stuff, and some of these things are HPC problems themselves. And there's a subgroup attached to the blockchain energy thing that are looking at how do you simulate the whole grid and power thing, So there's lots of people working in parallel on the same problems. It's trying to get them all to talk to each other is difficult.
Okay, well, yeah. So I'm wondering if we can get into if we can get this hardware completely open hardware in place with open BMC and everything, and it starts there, then people have something to actually start playing with, and then hopefully the open community can rally around.
I would say there's a bit of a disconnect between the power you're computing and the power in the grid, because usually you put uninterruptible power supplies in there to make sure you get 100% uptime.
He was talking about all of the aspects of that as well. It's obviously a huge.
And there's a separate, IEEE group looking at virtual and spinning reserve type machines. So how do you create something that looks like a big spinning generator, artificially, which just gets you back to how to simulate the whole thing. So I mean, there's lots of bits and pieces, but one of the pieces is just simulating the whole grid and how you do the energy sort of management. And that's a big simulation problem which you want HPC for. So it kind of sort of circles back on itself.
Right. Oh, and I should mention, Kevin did help me out. He did point me towards somebody that is a company that specializes in helping you get government funding, like SIBRs, etc. Called Eagle Point Funding, I think they are. Is it Eagle Point?
Yeah. The problem with them is they do ask for quite a lot of money. So
yeah, they want 50K from us.
Minimum, usually.
Make a load of boards.
Yeah, so it's a question of if you've got somebody who's got deep pockets that's wanting to sell a lot of hardware, we can help them get that done. If we get the grants from the government to go build something, somebody has to manufacture it. they'll make the money, but generally the manufacturers are not the people who are inventive and spec the system.
Right. So funding would give us a little bit of a boost in at least turning some of this into reality when we got to spend real dollars on PCBs and stuffing boards and not in the likes. Okay, I don't want to dwell any more on that, but again, that's something I'm trying to work in the background. But if anybody has any connections, or your companies maybe have to help us out, then that'll be good. So I'll just go through these. Libra BMC experts for sideband management implementation. So the interested parties there, well, that I know of, they're active in Libra BMC is we do have Xilinx, the FPGAs, their FPGAs, and we also have Lattice. in terms of real estate space and small devices, Lattice seem to have a better solution from what I've been looking at. And so I've been speaking to Lattice, and they are active in the Libra BMC side. They do a lot with I2C IP in their FPGAs, and so and I've spoken to them, and it looks like we may be able to get a resource that will join us. So I'm hopeful that actually Lattice could give us a nice schematic. I mean, my basic block diagram in my head at the moment, or I've got it in a 3D model at least, to manage all the sidebands of all the connector I/O is with like 10 or 11 Lattice FPGAs that I've got down there already. If we can make sure whatever we put down has the hooks to support Libra BMC implementations, then I think we'll be in good shape. So I'm hoping. I'll just put Alan's hoping for support from Lattice. So we shall see. But that's and Paul, I don't know if anyone in Xilinx actually owns this, and whether there would be a motivation for them if Paul's still on. He's still on, Paul.
You mean for a BMC?
For the Libra BMC side of things, is there anybody in Xilinx doing anything on that?
I mean, there are. I'm not sure. I mean, people do use Xilinx devices for BMCs. It's more niche applications for sure.
Yeah.
But yeah, I mean, that's.
I think the problem with the Xilinx is you don't do small enough devices and packages to squeeze it on the board. I'm using the
That could be
devices because Lattice acquired Silicon Blue, which is a really tiny
Yep.
device for mobile phones.
Yep.
So I'm using that class of device.
Understood.
Which then I can sprinkle around the connectors. But yeah, if Xilinx were interested, or if I'm missing something on the small devices, then that would be a possibility as well. On the clocking side, sorry, was that something?
I was going to say, Alan, do you have a contact at Lattice? I have some names I can give you if you don't.
That might not be a bad idea, Todd. I'm going in through a guy on the sales side, Brian Mink, and he's connecting me up with apparently somebody's been assigned this work and focusing on the compute side, so and on the Libra BMC side of things. So, but yeah, the more names, the merrier, actually.
All right, I'll send you an email. Sounds good.
Clocking experts. So we're going to need clocking capabilities, especially for the Xilinx device, going to be able to support 112 gig. And I think I selected a slide. I've got a Scilabs clock tree that I did put together just by myself. Scilabs tend to be the premium of clocking devices. So I'm not sure whether they would be willing to help, or they just say we're the best, use ours, put them down, and pay us lots of money, and or we could get them to help us. So. But I'm sure there are over 112 gig clocking solutions by now. But yeah, so just on clock trees, that may not be too much of a problem. But implementing and testing these will be and testing clocks.
I've got some tech for like modeling clock trees and stuff with power and timing together. If anybody's interested in developing it.
Oh, you've got some tech. Okay.
Well, there's a modeling technique you can use where you combine timing and power stuff in an analog type simulator, and it'll give you things like spread of timing analysis, so you can tell how much jitter you can tolerate and things like that.
Yeah, there's a guy that specializes in that. Here in Westlake in Los Angeles, he's written lots of papers on the power and on the jitter side of things.
I kind of do it from like Monte Carlo of the analog description of the wiring, and it's kind of automated. And
right. Okay.
haven't built it because I haven't been paid to build it.
Right.
But if somebody can find a DARPA grant or something for, we can go build that one. That's a good
Yeah,
HPC problem.
right. Maybe outside the scope of what we're trying to do here. But once you've done that, like, we'd be very interested.
Yeah, it's really part of the CDX group rather than this, but if anybody's interested, we can go do it.
Okay. On the mechanical side, so what I've been thinking on the mechanical side is we're sort of taking the same strategy as they did with OAM, the OCP accelerator module. Is they didn't really start with the chassis; they started with the module itself, and then everything grew from that. We have a desire to have 8 of these modules on a nice cold plate and plugging into the OAI chassis. But I think if we got one of these 2 modules, being able to just power up in a nice little standalone chassis box in some sort of kit form, so an engineer can have it on his bench, and it's got less like I was thinking we could do a single module and a dual module, so we could put one power 10 next to one FPGA, or a power 10 by itself, or an FPGA by itself. And I was thinking if it was in like a little self-contained unit, we could maybe use one of the liquid cooled kits for GPUs in your PC, from like Corsair. They do kit form versions, so we could buy the radiator and the water pumps and all that from them, and actually just have the cold plate design just feeding a single module or the dual module setup. And I was thinking that some of the IO, like we could have the FPGA, the 112 gig network IO, we could put to QDDs or OSFPs coming out of a tiny little chassis. So it was be like a standalone box with the E3 modules or the NIC 3.0 modules plugged in the top. You could have yourself a nice little bench setup, a bit like a Raspberry Pi for HPC. So that's, and I was thinking if we could make these pieces in kit form, so some mechanical contributors on that would be good. So we can actually build up some concepts on the chassis side. That could be hand in hand with some of the thermal experts. So the thermal and mechanical are going to be a little bit coupled together here. That's, and to Roger's point earlier, is he's doing load slammers where he's load slamming up to 1 kilowatt of power. So you can't load slam these sorts of powers unless you can really cool them at the same time. So this would be a nice infrastructure for cooling that as well. So that's that. I thought that might be a nice place to start before getting our heads too far over our skis and just trying to take 8 of these modules and plug them straight into an OAI chassis. So that was the thinking there. So anybody on the mechanical? I don't think we have any mechanical people here. I obviously, there's Philippe, you're on. Is Philippe still on? Oh, we've lost Philippe. Is there anybody who knows anybody or thinks they can help out on the mechanical side of things?
Those guys are hard to find.
Alan,
Yeah. Sorry.
Oh, sorry. Go ahead.
No, carry on.
I can look at like Cool IT, looking at when we look at the thermal. If we look at the thermal aspect of things, also looking at mechanical retention as far as the actual cold plate connections go.
All right. Okay.
If you can send out an email for the mechanical ask, I'll send it to the people I know at the ASME.
Yeah, actually, I've got this separated into two separate pieces here.
Yeah, I know,
Yeah. So
I know at least I know at least one person that was working on like thermal issues for like Dell in the mechanical engineering space. I can't remember what she's doing now, but you know, so there's a few people like that on the ASME mailing list probably.
Right. Yeah, there's a couple of things. So because we have the connectors underneath the processors, the traditional through-hole mechanical retention of the connectors is not necessarily gonna work. And so that's one thing, is how do we keep those connectors nicely in place, not be torn off the board without the need for through-hole. And you know, that's where a little bit of mechanical skill, I don't think is insurmountable based on people I've talked to. But that would be good to get a nice, elegant.
Well, I think there's a similar issue with like using interposers. You can't really, you don't get a lot of mechanical strength in an interposer, so you got a similar problem of how do you pack them up and plug them in.
Yeah, exactly. And then I said, yeah, about the single and dual HPCM carriers, so sort of bring up enclosures for prototypers. So on the thermal side, so thanks Callum from Cool IT. I was on the cooling of these little single and dual modules, we would only need to be in the sub 500 watt range. And I guess I was thinking of if we could leverage, if we could just design something that could leverage something that's off the shelf from you know, from the likes of these kit providers for GPU, because they're relatively cheap or very cheap compared to trying to design something new. So when they're in kit form, at least maybe we can just build our own little module that then can hook into their kits. I don't know if that's something that you guys at Cool IT would do, Callum, or not, or could help with, but that may keep it simple and low enough cost for these little prototyping units.
Yeah, I think that's a good idea, because the alternative, you'd have to have some sort of CDU and actually have like a bit of a fluid network. So if you have an all-in-one cooler, like you mentioned, that would be good for.
Yeah, Corsair, I believe, where I found on the web, they do kit form, and they do little sort of adapters for all the different GPU cards in the rest of the pumping kit and the radiators. So I thought, well, if we could just design the adapter for these modules for the HPCM for the two designs, and then we could plug into the Corsair kit. That would be one way.
Yeah, we can definitely, I can look into that. If you want something off the shelf, that's probably the easiest. But yeah, Cool IT, we supply to some of those consumer customers like that, as well as designing.
Oh, great. Well, if you already have the pieces from what you supply, and we could muscle up something from yours, then even better.
Yeah.
Okay, sounds interesting. Great, thanks. Signal integrity expertise for the SI channels. We have had support from IBM on doing some analysis of the short channels in the past, which has been useful. Might be difficult to continue to rely on those guys, but yeah, if there's any additional signal integrity experts out there that have all the tools so that we can analyze the channels, that would be great. And that covers most things. I don't know if I'm missing anything. Any comments on anything I'm missing? Okay. Okay, just in the last 5 minutes, if we can maybe get a forward-looking agenda, if we can start to put some topics in there where people can start to talk about a few things, that would be good. You know, as these activities get going. Based on what we've discussed today, just reaching out a little bit to you guys, is well, any volunteers on presenting at one of these next meetings and showing what you've done? I mean, Roger, it sounds like you've got some stuff moving on. Do you think in a few weeks you would be able to share what you've got and sort of encourage other people, or Todd on the IBM side, the open power side, is there anything maybe you can present in a few weeks' time of information we've got from open power that maybe help us get moving with the Power 10 module? Oops. All right, Roger's gone, and so's Todd. Damn. And Chris, do you think that Chris, you're with Roger, aren't you? Is that something you think you guys could present on in a few weeks?
Yeah, I think so. I think we can have some mock-ups and such.
Okay. So to possibly program analog. Okay. I'm going to put IBM. Oh, sorry. I'm going to put IBM down. Not open power down. I'll actually put it as open power because that's who Todd works with. And anyone else? Can I persuade anyone else to, or can we invite anybody else? Does anybody know who we could invite along? Maybe a PSU company presenting a power tree. These I'm just sort of thinking off the top of my head. Maybe Lattice presenting MC solution. I'll put ideas. I put this as ideas for future meeting presentations. Okay. Anything from anyone else here? Michael, do you see any? I mean, from Samsung's perspective, do you see this as useful for showcasing your CXL.mem modules?
Yeah, I guess so. And I think, in terms of that module, I'm not sure we just provide that one if you need for this mission. So
is that module, the CXL.mem module that you press released, is that something you could talk a little bit more about in one of the forward meetings?
Sure, yeah, I can update, maybe like CXL side update, something like that.
So if I put CXL update, including Samsung's CXL.mem E3.S module.
Yeah, actually, I think the February 25th, there's one guy from Samsung, David Wang. He's gonna update about this topic in the ODSA.
Oh.
So that's actually February 25th. The ODSA.
February 25th.
Yeah. So, I don't know, it can do it again for HPC, or maybe I can update.
Yeah, maybe you can give an update, or maybe we can even Well, see how relevant it is, but either you could give a boiled down update, or we could just play his recording from ODSA, if it makes sense.
Okay.
If it's quite applicable to what we're trying to do here. If it's wide ranging, maybe you could boil it down to just the focus of where it could be useful here in this work group.
Sure. Yeah. The ODSA, they want something like, in terms of die-to-die interfacing perspective.
Right.
They want to get some idea regarding this CXL solution. But for us, for HPC, more like a kind of, the product like spec on the CXL.mem.
Right.
Solution. Okay, great.
Yeah, obviously on the CXL, like the host connection, so our traditional PCI host connections, if they get CXL enabled by some switches, etc., then that will be interesting to hear about, or processors that could. So yeah, in general, how could CXL fit in with HPCM would be a good topic, for sure.
Okay, got it. Yeah.
Okay, thanks. If I can maybe just quickly go around. Brent, do you have any questions or input that you think, or topics that we think we could get people talking about? No. Any updates from anyone else? Paul, is there anything else to add on the Xilinx module? Do you think we've got things covered? Are we missing anything? Okay. Oh, I just realized we're 9:03. Apologies, guys. Okay. All right, guys. Thank you for today, and hopefully we can move the ball forward. And if we can get something on the next month's meeting, or I'll give another general update on progress we've made between now and then. Okay. So thanks very much.